I welcome you all for this NPTEL lecture on earthquake resistant design of foundations. Today we are going to have 37th lecture of this course, which is on the Raft foundations, some numerical examples. Actually, we are going to have the last module of this course, which is miscellaneous, and in this module, what we are going to discuss is this is the last module that is the 6th module of the course, and under this module, mostly the things which we have not covered yet, we will talk. First, we are going to talk Raft foundations, some numerical examples, and then on shallow foundations on slopes. So basically, we have already talked about shallow foundation in the module 2. However, we discussed the Raft foundation, but numerical examples was not discussed. So we are going to talk about some numerical examples on Raft today. What we are going to cover in today's lecture is first for soil, an example of soil pressure, and then some example on design of Raft. So first one, that is example number 1, which is on the soil pressure, how to calculate the soil pressure. What you could see in this figure, there is a raft foundation, and this raft is below 12 columns. The load carried by each column is shown here in kilometer. So, and then the size of each column is also given, square column. Let's say these are, and the size of each column is 0.5 meter by 0.5 meter. So size of each column is same, but load carried by these columns are not same, as well as the locations is different. But it is quite symmetrical. So you have 3 columns in one row, and there are 4 rows. So total there are 12 columns here. What you could see that the columns at the ends are denoted A, B, C, D, E, F. Okay, so you have on the top is as well as this is plot basically. So you have A, B, C, D, E, F in the plot. Now, what has been denoted here? X-axis and Y-axis has been marked in this here. But you could see that this is the center of this foundation, and this is X-axis, this is Y-axis. Then we have tried to mark another way axis, X prime and Y prime, assuming the origin is at the bottom left corner. Okay, so that means this at this point. Let me point out this. So this, if you assume this as the origin, in that case, this is your X prime and Y prime. Now, as far the location is concerned, the center to center spacing between the columns is 8 meter in X direction and 7 meter in Y direction. In Y directions, you have because 4 rows are there, so you have 7 meters, 7 meters, 7 meters. So altogether, 21 meters is the total length in Y direction plus 0.25 and 0.25. So it will be 21.5 meters. While in X direction, it will be 16.5. The size will be 16.5 into 21.5 meter in the plan. So these are the dimensions. Now loads, as you could see that 400, 1500, 1500, 400. So these are the loads given here. Now what is the question? The plan is shown in this figure. Calculate the soil pressure at points A, B, C, D, E, and F. What are the loads, soil pressure coming? So for that soil pressure, as we discussed, because this is a rectangular, and so in this case, with all are in plane, same plane. So what you can have soil pressure at different points can be calculated using this equation, which we have already discussed in the theory, where Q is total load coming divided by the area of the raft. Then you have moment multiplied by, and X and Y are the coordinates with respect to the center, centroid points. So first we need to decide what is My, Mx, Iy, Ix, As far area is concerned, area of the raft is total 16.5 into 21.5. So this leads to the 354.75 meters. Now Ix, if you talk about Ix, so you could see here, this is B. B is 16.5 meter. So B is the width. So B is the width along X direction. Okay, and L is along this direction. So Ix is BLQ, where L is along this direction and B is along this direction. That means B is the shorter and L is along the. So B, when we find out, so B, the 16.5 meters along X direction. So you get this Ix value of Ix in this case is 13,660. Same way, Iy will be 1 by L, where L is in the direction of Y. So 21.5 into 16.5. So you end up. So you got the area, you got the Ix, Iy. Now let's see what is the value of My and Mx. To calculate the value of My and Mx, what is required? That you need to first calculate the eccentricity. Eccentricity in the sense, so for calculation of eccentricity, let's assume that this is the origin here. The origin is here with respect to, and then we can calculate. So assuming origin here, then total load in any case, irrespective of wherever you assume the origin, the value of Q is nothing but this is the total load. That means some of the columns 2, 3, 4, 6, 8, and 12. All 12 columns loads sum is 11,000 km. Q is My can be calculated Q multiplied by Ex, where Ex can be calculated X prime minus B by 2. Where what is X? How X prime can be calculated? X prime can be calculated simply. You have, let's say, all the columns multiply by their distance of their centroid for each column in the X direction divided by the total load. So what you get here, Q1 X1 plus Q2 X2 prime. So what you have, let's say, for first column, this 8.25. 8.25 is this for this row. At this row, you have two loads 500, 500, and two loads 1500, 1500. So when you work on this, 500, 500, and 250. Then 16.25, the last row and the first row. So you sum up all these and then divide by 11,000. So you get X prime 7.814 meter. So that means the location of the centroid with respect to this is at 7.8. So it will be somewhere here. So, and then if you have minus B by 2, B, where B is 16.5 divided by 2. So with respect to the centroid, this is on the left hand side, that means negative in X direction, minus 0.435 or roughly 0.44 meter, which is negative. Negative means it is on the left hand side of the center. Similarly, you can calculate the value of Ey also. But before once Ex is calculated, so calculate the first My. My is Q into Ex. Q into Ex. Ex is 11. Okay, so here it should be 11,000. So let me correct it here. It should be 11,000. Not 11. So it should be 11,000 into 0.44. So once more you multiply, so you naturally 0.44 half 0.4840 kilonewton meter. So you get the value of QMy equal to this. Okay. Then Mx will be Q into Ey, and this way you can calculate the value of Ey, y prime minus Ly, where y prime is calculated in the same way as we have calculated x prime, and Ey will be minus Ly. L is 21.5, so you get here 10.75, so 0.1 meter. That means Ey will be positive. So what you could see here, let me show this location of the centroid. So the location of the centroid is here. This was your centroid, and if we say this is the centroid with respect to geometry, and this is the centroid with respect to your masses. So that means your this all the four the mass will act at here. So you have this distance as a 0.44 meter in x direction, in y direction 0.1. So 0.44 meter and 0.1 positive direction. So what you have here, continue with this. So you have calculated. So when the value of Q can be calculated by using this equation. Now put all the numbers in this equation: 11,000, 340, 8050, 3665, which has been already calculated here, and the values of the Mx. Mx is coming here 1100, right? So 1100 into y. So what you ultimately get in this equation, because it was negative, so plus minus will be minus plus here 0.6 plus minus 0.8 y kilonewton meter per square. Here, one thing you need to understand that here x and y are the coordinates which are with respect to this center, not with this center. So now, once you have this equation is ready, then put the value of x and y according to, and you need to understand that for in this case, x will be positive for all these columns, 0 for all these columns, and negative for all these columns. Same way, y will be positive for all 6 these columns and negative for these 6 columns. So, for example, the value of a, okay, for a column, your x will be negative as well as y will x will be negative, but y will be positive. So once you put, but here because negative sign is coming, so once you multiply 8.25, 8.25 is this distance, and 10.75 is 7 plus 10.5 plus 0.25. So this way, both becomes positive and you get 36.8. Similarly for B, what you have for B? For B case, you have x equal to 0. But y will be for this column will be y will be same as 10.75. So you end up in this way. Now for C, this will be positive, x will be positive, and that will be same as 8.25. But because negative sign is coming in the equation, so you end up in this case. Coming to D, D again, x will you will have the x will be here in this case positive, but because negative sign is coming, and y will be now negative. So you end up 25.19. So that is this. Then for E, your x is 0 and y is 10.75, which is negative. So this becomes 0. So you end up, if I compare with this 31 minus 0.6, it was 0 here. So this is 0. Okay, and this was Q. Q is negative. So you end up in 30 point. So all right, this was actually, yeah, if we compare, this was negative here, this was 0 here. So 30.10. Then for Q, you got this number. Again, you put all the numbers here. And in this case, what is left out is, let's say for x is for negative and this is y. So you end up here. So what you can see here, out of these A, B, C, D, E, F, you get the minimum value for C here, and maximum value you get is for A, in this case, this side. And because here, in this equation, minus sign is coming first. So as a result, you get these numbers here. All right. So this is ranging between 25.19, which is the lowest value, and then 36.81 is the highest value. Okay. Now continue with that. So this was this example gave you the soil pressure at A, B, C, D, E, F. So this way we are able to calculate the value of soil pressure. Now the second example, which is on once we calculated the soil pressure at ABC, then what is has been asked that divide this mat foundation shown the same foundation into 3 strips. And what are the 3 strips? It is first strip is A, G, H, F. Okay, so A and F was already there. We put two more lines. One is GH, another is IJ. So A, B, C, D, E, F was already. Then GH and IJ are shown in this plot. So first strip is AGHF, and width of this strip B1 is nothing but half of 8 meter, that is 4 plus this 0.25, so 4.25 meter. Now coming to the second strip is GIJH, where you have up to center 4 meter and another 4 meter. So you get the strip width B1 as 8 meter. Then another ICDJ, third strip is width is 4.25 meter. And using the result which we have calculated it in example 1, determine the reinforcement requirement in the y directions. Actually, before reinforcement requirement, what we are going to calculate, we are going to calculate what are the bending moment and shear force diagram. So we will restrict ourselves to calculate the shear force diagram and bending moment diagram for these three strips. When shear force and bending moment diagrams are found out for these strips, then we can determine maximum bending moment as well as maximum bending moment will help you to find out in the designing, that means for finding the reinforcement. So our objective will be here to find out the shear force diagram and bending moment. So let's work on them one by one on one strip. So for the first strip, AGHF, what you have average soil pressure. So first what we are going to discuss is determination of shear and moment diagram for these strips. So average soil pressure, which is denoted as a Q average, and Q average is Q at A divided plus Q at F divided by 2. That means only for this finding this average at the end columns, at the end of this column for this strip. So average Q at A, so A, Q and 36.81, and if you have from A and F 35.09, so you add, and then once you add and divide by 2, average 35.9. Total soil reaction will be the area of this strip, which is calculated here. If you go, area will be, what will be the 4.25 multiplied by the length, which will be 21.5. So you have 21.5 into 4.25 multiplied by this stress, so you end up here in total soil reaction equal to 30 to 85 km. Now sum of the column loads on the strip will not be equal to Q average into B1 into L. So Q average into B1 into L is the total load. But if we sum of the column loads which are coming on this strip, what are the column loads which are coming on this strip is 4 column loads. 400 plus 15, so 1500 will be 3000 and 400, so 800. So the Q average into B1L will not be equal. Why? Because the shear between adjustments is not being taken into account. And for this reason, the soil reaction and the column loads need to be readjusted. And how you adjust those? First, average load. Average load is total column loads and loads due to soil reaction. Load due to soil reaction we have already found out. Column loads is sum of the all column loads 3800. If we divide it by 2, then you get the average load. So now the further calculation should be done with respect to this average load 3542.5 km. So to account for this, now what you do, you get the modified Q average. Here you find the Q average value 35.95 when you have the total solution 32.85. But when you have this 35.42, so then Q average will increase 35.42.5 divided by this total solution multiplied by the Q average will give you the modified value. So in this way you find the modified value. So this was the modification in the soil pressure which you have find out. So instead of 35.95, soil pressure you should be used is 38.76. Then the column loads can also be modified, which is because and this need to be modified by multiply by each load by a factor, because ultimately you want to get the average load 3542.5, but the total load coming on the columns is 3800. So the factor, which is nothing but the ratio of these loads, is coming 0.9332, and you use this factor. So you multiply the load on each column by this factor 0.933 for the given load and find out what are the loads they are. And the load per unit length of the beam acting will be B1 into Q average modified, and B1 is Q average is 38.768. We have already calculated. B1 is 4.25, so you get 164%. So with this data which has been collected, what you do? You plot shear force diagram and bending moment diagram. So before you plot the shear force and bending moment diagram, so the data shown is here. That here you have load per unit length of the beam is applied from the down is 164.76. So UDL is acting from the down. Why these loads are coming? This number is nothing but 400 multiplied by this factor. So factor is 0.933. So once you multiply 400 by that factor, then you get here the same at the both ends. When you multiply 1500 by that factor, then you get these two loads. So all you have the four loads here. Then these are acting from up, and then UDL is acting from the down. When such loading is applied, then what you can have the shear force diagram like this, where this will be this UDL, and at this point you will have a sharp reaction. This will come down, and the sum of these two will be 372.25. Then again it will continue to increase because the load is acting in this direction, and once it is acting, then again coming down, continue with that. So sum of these 821 and 576 is 1308. Okay, and the same thing is here. So this is the shear force diagram. Similarly, you can draw. So maximum shear force is coming here. In this case, 821.65 is the maximum shear force. While the maximum bending moment also can be derived. So you will have parabolic here, and the maximum you got here. Then, due to the presence of this load, this UDL, and this goes to maximum here, this point which is corresponding to this point, you get 727.5. So the maximum bending moment is this, and you need to design your this raft according to this for this strip. So for the AGHF for the system, these are the shear force, maximum shear force, and maximum bending moment diagram shown here, and accordingly reinforcement need to be done. So this was the case when you have the first strip, that is EGHF. On the same line, we go for another strip, the middle one, GIHG. Okay, and naturally for that you use the average load coming on column B and E. So let's work on this. So for this case, what is Q average at V and E? It comes 31 kN per meter square, and total cell reaction will be total area multiplied by this Q average. So because now what is the issue here? So area is increased compared to before, and once area is increased, what is area? 8 into 20, which is quite high. So you get total soil reaction quite high, while total column load is 4,000 kg. Now in this case, your soil reaction is more than the total column load. That is the difference in the earlier step. So average load will also be more than your total column load, and Q average modified can be find out total average load divided by the total soil reaction. So this comes out 27.12, while load per unit length of the beam is equal to B1 into Q average modified. So 8 multiplied by this, so you got here, and factor where total this average divided by the total load. So each column load need to be multiplied with this factor 1.165. And what are the loads coming? That is, you can see it is 500, 1500, 1500. So modified will be more than that. They need to be multiplied by this factor 1.165. So the details are shown in this figure. 217 kN. This is acting here. So, and this is 500 multiplied by this factor. This is 1500 multiplied by that factor. All these are there, and then you have this again shear force diagram. So the maximum value of shear force is coming. In this case, is here. So this is the maximum value of shear force, 990.17, and this is the maximum value of your bending moment diagram, 1620. So this naturally the design will be governed, or reinforcement should be enough to support these maximum values. All right. So this was the second strip, where the strip considered was the load coming was quite high, GIGH. Now let's come to the last one, ICDJ. Okay. So in this case, when you talk about ICDJ, so these are the details given here. You need to consider the load at point C at D, and point C and D can be seen here. And this C and D is the last columns here. This is your C and this is the D. And once you have this C and D, then divided by 2 will give you the value of the Q average. And this average should be multiplied with the width and length of the strip. So you end up with 2380 kilonewton. And total load coming on the strip is 3200 kilonewton, which is higher than the total cell reaction. Then average load can be found out by summing of these two divided by 2, which is so average is higher than the total cell reaction, but less than the total load coming on. So this way you can find the modified the average value of Q average modified. Just simply multiply by this and average load divided by the load which you have find out. So it will increase, while the factor which need to be multiplied by each, so it will be the average load, that is 2C790 divided by 3200 is the sum of all the loads. So all the loads should be multiplied by a factor of 0.87 before the calculation. And at the same time, load for impedance B is equal to B1 into Q average modified. So B1 is 4.25 multiplied by the Q average. So this is 30.53. So we got 129.75 kilonewton per meter. And this factor, once you have this factor, this is the load acting on the down, while the factor is, we already discussed, 0.87. So for this strip, ultimately what you do here for this strip, you have again this is 129.75 and 13 when you multiply by each load, for example, with this factor of 0.87. For example, you multiply by what are the loads here? 450. First load is 450, right? And then 1200 and 350. So 450 multiplied by this factor. You got here the last one. So this is 450 multiplied by 0.872. And this is then this is 350 multiplied by that factor. So you got here, and as these are 15 multiplied by this. Then you, for this loading, you draw the shear force diagram and bending moment diagram. So you end up here. Usually the sum of these two should be, that will be sum. Same thing is here. So in this case, the maximum shear force you are getting is here 635.63. Okay, and minimum shear force and maximum bending moment is here. Sorry, maximum bending moment will be not here. Rather, you have maximum bending moment here, 1196. One thing I would like to point out here, that you could see here that in between the shear force is not same as was the case earlier. And the simple reason here, even because load is not symmetrical here. It is what you could see here. The load is though in between, it is okay, 1200, but the ends it is not same. It is 450 and 350. So unlike other two strips, it will not be symmetrical. So what you have maximum value in this side is 635, but here 540. The same thing is for bending moment diagram. So this way you can calculate bending moment and shear force. Continue with that. The last part of this is determine the thickness of the mat for this section for the column load of 1500 column load around that. So for this problem, the critical section of the diagonal connection shall be at the column carrying 1500 kg of load at the edge of mat. So critical section will be where the 1500 kilonewton load is acting near the edge. In this case, total periphery along this column, there is B naught, is calculated here. 0.5 meter is this distance. So you will have 0.5, and this is D by 2 here. D by 2 this distance. So this will be 0.52 D by 2. And in this direction, it is D by 2 in this case. In this case, so you got 0.5 plus D and 0.5 plus D by 2. So once you sum up all these, then you end up here 1.5 plus twice D equal to B naught. So B naught is this. Once you calculate the value of B naught, determine the effective depth D of the mat by checking for diagonal tension shear near various columns, and according to American Code of Concrete Institute Code 31895, for the critical section, the value of U is given by this relation E naught D, whatever 5.34. What is U here? U is factored column load, which is meganewton of column load into load factor. So here, what you have load factor is given to you 1.7 in this. So 1.7 multiplied by the column load given is here, 1500 column. So you get the factor load as 2550 kilonewton, that is 2.55 meganewton. Once you have this U value is given known to you, then you put all the numbers in this equation 2.55 V0 D. V0 D is nothing but 1.5 plus twice D, and then D is again 0.85, 0.34 into FC prime. So FC prime is already given to you. So with this, ultimately, then you end up the value of D equal to 0.68 meter. So here, once you solve this, so D will be coming 0.68 meter. So thickness is coming 0.68 meter here, and assuming this thickness, what you have a minimum cover of 76 mm over the steel reinforcement, and also assuming that the steel bars to be used are 25 mm in diameter, the total thickness of the slab can be found out from here. Total thickness will be, this is the D value of D. Once D is calculated, then you assume 76 mm cover, that is 0.076 meter, and the steel bars to be 25 mm in diameter, assuming 0.025. So total thickness required is 0.781 meter, which is approximately 0.8 meter. So thickness should be 800. Thickness of the mat, at least thickness of the mat should be 800 mm. Yeah, which will satisfy the wide shear condition across 3 stitches under construction. So this was our example set. And with that, we have covered some numerical examples on Raft foundation. Thank you very much for your kind attention.